This is section 2.5, zeros of polynomial functions. The rational zero test. Before we begin, let's talk about a couple of important existence theorems. The first is the fundamental theorem of algebra. That says that if f of x is a polynomial of degree n, where n is greater than 0, then f has at least one 0 in the complex number system. So essentially we're saying whatever the degree of the polynomial, we have at least one 0. The linear factorization system says if f of x is a polynomial of degree n, where n is greater than 0, then f of x has precisely n linear factors, and they're going to be written in this form. Now keep this in mind because this one we are going to be using. F of x is equal to a sub 0, which is just some constant, and then these are all of the linear factors, and there are n of them. Now keep in mind that C1, C2, and so on, those are all complex numbers. We did talk about complex numbers being the form a plus bi, but it could be just the real portion, it could be just the imaginary portion, or it could be a full complex number. In this section, we're going to be learning a lot of little tidbits that are going to help us to factor polynomial functions. So we've already learned how to factor them. We've already learned a few strategies, but now in this section, we're going to focus a little bit more on tips to narrow down the number or types of factors that we can have. So the first of those is the rational zero test. And that tells us that if we have a polynomial in this form, so this is the non-factored form, and it has integer coefficients, so all of the a sub n minus 1 are integers, then every rational zero of f has the form p divided by q, where p and q are no common factors other than 1. P is a factor of the constant term, so p comes from here, and q is a factor of the leading coefficient, so q comes from here. So we're going to use the rational zero test to determine, just to practice together, the number or the possible factors of our polynomial 2x cubed plus 3x squared minus 8x plus 3. So what we're going to do is we're going to make a fraction, and on the top we're going to write any factors of p, which is the constant. So 3 has to have factors of plus or minus 1 or plus or minus 3. And then beneath that, we're going to look at any factors of q. So we're looking at just the 2, so the coefficient of 2. So I shouldn't have circled the x cubed. Factors of 2 are plus or minus 1 and plus or minus 2. So when I simplify this fraction, I'm just going to write out the list. So I could have plus or minus 1 over 1, which is 1. And I could have plus or minus 1 over 2, which is plus or minus 1/2. I could have plus or minus 3 over 1, which is plus or minus 3. And I could have plus or minus 3 over 2, which is plus or minus 3/2. So what we've done is we've said we know that there's going to be 3 zeros. We don't know how many are rational, but if we do have a rational, it's going to be one of these 8 numbers that we've just come up with. We're now going to use Desmos to help us determine which of these are zeros. Now you might be saying, well, Professor Brame, why don't I just come down here and click on these and determine the actual values? And you could, of course you could, but we want to learn about what the rational zero test tells us. So we're going to actually use the left-hand side of Desmos to determine. So we're looking at the x values of plus or minus 1. So I'm just going to do f of 1, and I have just already found that I have 0. Now, I could try f of negative 1, but I can see on my graph it's definitely not going to be that. But again, I can try it, f of negative 1, and I can see that that value is 12, so that's not going to be a 0. Then I'm going to move on to plus or minus 3. So let's use 3. That value is 60, so that's not correct, so negative 3. and that is a 0. And then I'm going to keep going. So I've used plus or minus 3. Let's do f of 1/2. And now we have found all of the zeros. Again, yes, I could have cheated a little bit and just graphed it and determined the zeros, but this gives us a great idea as to how we can use that theorem. Now keep in mind that if I was then asked to factor, I should be able, to factor. I'm going to make a new function g of x, and I'm going to call it x minus 1, so x minus my first 0, x minus negative 3, which is x plus 3, and then instead of x minus 1/2, I'm going to call that 2x minus 1. And we can see that that is the exact same graph as the original graph, so I've written it both in the standard form and in factored form. I have one for you to try as well. So this is find all the real solutions to the polynomial function f of x is equal to negative 2x cubed minus 5x squared plus 15x plus 18. Again, I encourage you to use technology, but don't use technology to make you dumb. Use technology to make you smarter. So use that rational zero test to come up with all of the values using 18 as p, so all of the factors of 18, 1, 2, 3, 6, 9, 18, and all of the factors of q, 1 and 2, and use Desmos to determine which ones are real factors and go from there. When you're ready, press play to see how you did. So, first step, list out all of the possible factors. Next step, use Desmos to determine what real solution you have. So I only found one rational 0, which was f of negative 1 is equal to 0. But they asked me to find all of the solutions. And so all of the solutions means I have to keep going. So I am going to use the fact that I know that I have a 0 of negative 1. I can use synthetic division to determine what's left over after I factor this. So again, remember this would be like x minus 1 is a factor, and negative 2x squared minus 3x plus 18 is a factor. Now I have to continue to factor that quadratic, and I chose to use the quadratic formula. And so I came up with, two solutions that are irrational solutions. So they're real solutions, but they're irrational. They're not rational. So I have one rational solution, which is negative 1, and then I have two irrational solutions, which are 3 plus radical 153 divided by negative 4, and 3 minus radical 153 divided by negative 4. Conjugate pairs. So again, recall that this entire section is all about trying to find the zeros or factors of polynomial functions. So far we've talked about a polynomial of nth degree has exactly n linear factors. We talked in a previous chapter or section about a polynomial of odd degree. It has to have at least one real factor, rational or irrational. But to add to this list, we have complex factors that occur in pairs. And what that tells us is that if you have a plus bi as a 0, then you also have the complex conjugate of a minus bi as a 0 of the function. That's going to be helpful because if we are told that we have a 0, we know that we're going to have the other 0 as well, and that cuts our work in half. Now stick with me on this one because I did start us off with sort of a more difficult example, just because I don't want this video to be 45 minutes. So we're trying to find a cubic polynomial with real coefficients that has 2 as a 0 and 1 minus I. Now cubic tells me that the highest degree is 3, which means there's 3 real zeros. So I'm going to write this as x minus 2, and then I'm going to write this as x minus 1 minus I, and then the complex conjugate of that is 1 plus I. So I'm going to write that as x minus 1 plus I. Now, it looks a little ugly and messy, but just wait, it's going to get worse. So what we're going to do now is we're going to multiply this out. Now, keep in mind, there is in fact an a here. But because it says find a cubic polynomial, we don't have to find one that specifically fits a certain input-output. We're just going to let a be 1. So we're just going to let that be 1 for now so we can focus on the more difficult part, which is multiplying these binomials. So again, we have f of x. This one we're going to keep till the end because we want to multiply these two together. So let's focus on these two. If I'm foiling, and I'm going to write a lot of steps here just so you understand exactly where everything comes from. X times x is x squared. X times minus 1 plus I is minus x times 1 plus I. And then minus 1 minus I times x is minus x times 1 minus I. And then minus 1 minus I times minus 1 plus I is plus 1 minus I 1 plus I. So even though I've completed a step of work, it looks like I'm going in reverse, it looks like I'm going backwards, and that's normal. Again, if you're very good at mental math, you can skip some of probably this step that we just did and do some of that math in your head. But for the sake of this being the first time that we're doing it, I'm going to write out all the steps. X squared doesn't change. This is minus x and minus xi. This is minus x and minus xi, so plus xi. And then I'm going to FOIL this. So I have plus 1, and then I have plus I, minus I, minus I squared. Okay, again, it's not getting better yet, but it will. So here I have a minus xi and a plus xi, those cancel. I have a plus I and a minus I, those cancel. And I'm going to call minus I squared as minus negative 1, which is plus 1. So now let's continue. Again, don't feel like you have to write all of these steps, but you have to write some of them so I know you're just not plugging this in somewhere. This is x squared, and then I have minus 2x's. And then I have a plus 1 and a plus 1, so I have a plus 2. So if you go straight from this all the way to here, I will assume that you didn't do that math yourself, and you should get used to doing math yourself. Now from here, all I'm going to do is distribute. So we know how to do this. We're going to take x times x squared, that's x cubed. X times minus 2x, x times plus 2. Now I'm going to do the same thing with minus 2. So minus 2 times x squared, minus 2 times minus 2x, and minus 2 times plus 2. And finally, we can combine like terms. So I have x cubed, I've got minus 4x squared, I've got plus 2x and plus 4x, so that's plus 6x, and then minus 4. Now again, I'm going to stress to you, this is all of this times some value of a. For the sake of simplicity, we left a to be 1 for now, but on our next example, we're going to actually use a given point to determine the value of a as well. So another practice, what I would really like for you to do is to try to do that first part, the part that we did together on the last question. We're given that it's quartic, but they really have given us all of the zeros because we know that the other 0 is going to be negative 2i. And this one will be much easier to multiply because we don't have a binomial within a binomial. So if you could do that first part and find the polynomial, we'll do the second part together. And if you're still stumped, that's okay. We can do the whole thing together. So the first part is go ahead and write out a, because this time we are going to use a other than 1, and then x minus 1, that's from the 1, x minus negative 2, so that's x plus 2, x minus 2i, and x minus negative 2i, or x plus 2i. Now, as you're multiplying this, it's easiest to multiply the two normal binomials and the two imaginary binomials separately. So I'm going to multiply x times x is x squared. I've got plus 2x minus x. And again, if you need to write plus 2x minus x, do that. And if you can in your head say that's positive x, do that. And then minus 1 times 2, that's minus 2. So I have x squared plus x minus 2. I've got my a on the outside, and now I'm going to do the same thing here. X times x, x squared. Now we know what's going to happen here. We're going to have plus 2ix minus 2ix. So I'm not even going to write those. That's always going to happen. And then I have minus 2i, and plus 2i gives me minus 4i squared. And again, if you need to write minus 4i squared and then simplify it on the next step, you can. I say I squared is negative 1, so it's negative 4 times negative 1. That gives me plus 4. So again, I'm just trying to save myself having to recopy a lot of things. Now from here, I have to do the work. I have to distribute. So I'm distributing, oops, this was an x squared, I apologize. X squared times x squared is x to the 4th. X squared times plus 4 is plus 4x squared. Now I'm going to distribute x. So x times x squared is x cubed. X times plus 4 plus 4x. Minus 2 times x squared minus 2x squared. Minus 2 times plus 4 is minus 8. Now we're simply going to simplify. So x to the 4th, x to the 3rd. I've got a 4x squared and a minus 2x squared, so I have plus 2x squared. I've got plus 4x, and I have minus 8. Now on our last question, that's as far as we had to go. On this question, we are given a little bit more information. It says f of negative 1 is 10. So I'm going to use that to determine the value of a. So if f of negative 1 is 10, then 10 is equal to a, and then I'm replacing x with negative 1. And I'm going to do that for all instances of x. And then I'm simply going to evaluate. So I get 10 is equal to a, negative 1 to the 4th is positive 1, negative 1 to the 3rd is negative 1. 2 times negative 1 squared. Negative 1 squared is positive 1, so that's plus 2. I have 4 times negative 1, so that's minus 4, and then I've got minus 8. And if I combine all of those together, 1 and negative 1 cancel. 2 minus 4 is negative 2, minus 8 is negative 10. So I have a times negative 10. So divide each side by negative 10, and I get negative 1 is equal to a. So my final solution is that f of x is equal to negative 1. Now you don't have to put the 1, you can just put negative. And then, where was my solution? X to the 4th plus x cubed plus 2x squared plus 4x minus 8, which is negative x to the 4th minus x to the 3rd minus 2x squared minus 4x plus 8. That is my final solution. Factoring polynomials completely. Before we factor completely, I wanted to give you two more rules that might help us. First is Descartes' rule of signs, and that says that if you have a polynomial with real coefficients, we can narrow down the number of positive real zeros or negative real zeros based on how many times the sign changes. So this is variations in sign of f of x. So if you've got a plus and then the next one's a minus, that's a sign change. And then if the next one's a plus, that's a sign change. So basically you're counting up the number of sign changes. And so if we're looking at f of x, the number of positive real zeros is either the number of sign changes or less than that by an even integer. So if, say we had 3 sign changes, it had to be either 3 or 1 positive real zero. Now to do to do the negative real zeros, we would have to determine f of negative x. So really we would just determine the signs. We wouldn't have to do a lot of work. We would just look at the signs changing if we replaced x with negative x, and that gives us the number of negative real values or negative real zeros. And again, it's that or less than that by an even integer. The other is the bound rules. And again, if you're graphing this to help you determine the zeros, you're probably never going to use this. But the bound rules say that if you take something and divide it, so if you use synthetic division, we have x minus c as a factor, and you use synthetic division, if c is greater than 0 and each number in that final row is positive or 0, then c is an upper bound. So you know all of the rest of the real zeros are going to be less than that. If c is less than 0 and the numbers in the last row are alternating positive, negative, and zeros count as either, then c is a lower bound for the real zeros. Now let's pull together everything we know about factoring. And when we are working through all of these examples, we're going to factor completely, but we're also going to find the zeros so that we know how those two are related. For the first question, I wanted to give you one of the zeros, and I wanted it to be imaginary. So, because we haven't practiced a question like this yet. So remember, my final solution is to find f of x is equal to, and then I want to write all 3 factors. Now, how do I know there are 3? Because it's a degree 3 polynomial. So we are given that 4i is a 0, so x minus 4i is a factor. And because that's complex, we can use the complex conjugate x plus 4i. So my work is very close to done. Remember, we also want to find the zeros, and the zeros would be 4i and negative 4i, and then something else. So what we're trying to do is find that something else for both. Now, how am I going to go about that? Well, in this case, I'm actually going to multiply out the 2 zeros, or the 2 factors that I know of. So if I multiply this out, I'm going to FOIL it. First times first is x squared. Outside is plus 4ix. Inside is minus 4ix, which will always happen with a complex conjugate. And last is negative 16i squared. Well, we know the 4i and the minus 4i cancel. So I have x squared, and then this is minus 16, and then times I squared. Remember, I squared is negative 1, so it's minus 16 times minus 1, which is plus 16. So what I'm going to do with that is I'm going to divide. I'm going to see what's left over. That requires, unfortunately, polynomial long division. Even though we love synthetic, this one has an x squared factor. It's not going to work out exactly the same. So we're going to use long division. So again, x squared and 3x cubed. What would I take times x squared to get 3x cubed? Or if I divided 3x cubed by x squared, what would I be left with? And that would be 3x. So 3x times x squared is 3x cubed, as we wanted. 3x times 16 is plus 48x. Notice that we always line everything up correctly. Now I'm going to subtract these. So subtract, and it looks like everything cancels. So now I'm going to continue. I'm going to bring down the negative 2x squared and bring down the minus 32. And again, I'm going to focus on x squared and minus 2x squared. What would I multiply by x squared to get negative 2x squared? I would take it times negative 2. So negative 2 times x squared is negative 2x squared, and negative 2 times 16 is negative 32. And if I then subtract those, I would change the sign, and we see that everything cancels, and I get a remainder of 0. And it's important to understand that you should have a remainder of 0, because we know that 4i and negative 4i are in fact already zeros. It makes sense that I wouldn't have anything left over. So what this tells me is that my final factor is 3x minus 2. And my final 0 is setting 3x minus 2 equal to 0, which you can do that mental math if you'd like, or you can work it out. And x is equal to 2/3. So that's my final 0 is 2/3. Here's our next question, and you can see that we are not given any of the zeros this time, and that there should be 5 of them, 5 factors. So let's go ahead and see how you might start here. Remember, we're going to use the possible zeros. So we have 8 and we have 1. So I know that my factors of 8 are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. And my factors of 1 are just plus or minus 1. So these are my possible factors. And off camera, I just used Desmos to plug those in to determine some of the zeros. So again, you would use this function in Desmos, and then you would simply say g of 1, and it would find the answer for you, g of negative 1, and so forth. In doing that, I found that x equals 1 is a 0, and x equals negative 2 is a 0. So let's start with those and see what happens from there. So again, I'm going to use synthetic division because it's easier and faster. So I'm going to plug in a 1, and then I've got 1, 0 as a placeholder, 1, 2, negative 12, and 8. And then I'm just going to follow the algorithm that says bring down the first value, and then if it falls below the line we multiply, 1 times 1, and it falls above the line we add. So 0 plus 1 is 1, and then 1 times 1 is 1, and 1 plus 1 is 2, and 1 times 2 is 2, and 2 plus 2 is 4, 1 times 4 is 4, and negative 12 plus 4 is negative 8, 1 times negative 8 is negative 8, remainder of 0. I'm not even going to write that out, I'm just going to keep working. So now I'm going to use negative 2 to see what I have left and figure out where to go from there. So I've got 1, negative 2 times 1 is negative 2, I add them to get negative 1, negative 2 times negative 1 is positive 2, I add them to get 4, negative 2 times 4 is negative 8, I add those to get negative 4, negative 2 times negative 4 is positive 8, I add those to get 0. So now I'm going to see what I have left. I've got, we started with 5, so this would be 4, and this would be 3. So this is x cubed minus x squared plus 4x minus 4 is equal to 0. Now, this is 4 terms, and we said, okay, if you have 4 terms, you're going to need to factor by grouping or use polynomial long division. So I've only found 2 zeros so far. Let's go ahead and see if factoring by grouping works, because it looks like it's going to. What's a common term for x cubed and minus x squared? It's x squared, leaving me with x minus 1. What's a common term for 4x and 4? Well, that would be 4. So plus 4, and that would give me x minus 1. And remember, to factor by grouping, I'm going to take those outside terms, x squared plus 4, and then the common factor of x minus 1. So we know now that if I set each of these equal to 0, so I already know that x is equal to 1 and x is equal to negative 2. So x is equal to 1, negative 2. If I set this factor, x minus 1, equal to 0, I get x is equal to 1. So that means this one has a multiplicity of 2. Multiplicity just means it occurs more than once. And then if I have x squared plus 4 is equal to 0, then I get x squared is equal to negative 4. And that means x is equal to the square root of negative 4, which is plus or minus 2i. So then I have 2i and negative 2i. Now, factoring completely, again, I would say g of x is equal to, and then I'm just using each of those zeros. So x minus 1, and there were 2 of them. And then we had x minus negative 2. And then we had x minus 2i, and we have x plus 2i. So that's the complete factorization and the zeros. Here's one last question. If you're feeling confident, press pause, try this question on your own. If you're not, stick with me and we'll work through it together. So to begin this one, I wanted to include this question because it has a degree of 4, but there's only 3 terms, and those 3 terms have a degree of 4, 2, and 0. And the reason that's important is I can think about this as x squared plus 8x minus 9. And then that first term, when I factor, is just going to be an x squared instead of an x. So for a moment, I want you to think about how I would factor this trinomial. I would say, well, a is equal to 1, so that's going to be easy. I'm looking for numbers that multiply to 9, so 1 and 9, 3 and 3. And they need to have a difference of positive 8. So this has a difference of 0. 1 and 9 do have a difference of 8, but I want the difference to be positive 8, so I'm going to use a minus and a plus. So if I were factoring this, I would get x minus 1, x plus 9. So now back to our original question, I get x squared minus 1, x squared plus 9. So again, we're not done because we want it factored completely and finding all the zeros. So now I'm going to factor each binomial. So this is a difference of squares pattern, perfect square minus a perfect square, so it's x plus 1, x minus 1. And what am I going to do with x squared plus 9? Well, x squared plus 9, you can factor into x plus 3i, x minus 3i, but that might not be immediately obvious. So it might be that you have to come off to the side and say x squared plus 9 is equal to 0, x squared is equal to negative 9. Taking the square root, I get x is equal to plus or minus 3i, and there's your factors. So here's my factorization. This is g of x is equal to x plus 1, x minus 1, x plus 3i, x minus 3i. My factorization, my zeros is 1, negative 1, 3i, and negative 3i. Coming up next, we're going to look at rational functions.